Okay, let's dive into this. When you or I look at a digital coffee mug or a complex 3D shape on a screen, our brains instantly know exactly what it is, no matter what weird angle we're viewing it from. But a computer, it doesn't have a visual cortex. It literally just sees raw data. So how do we teach a machine to identify a 3D shape with absolute certainty? Well, welcome to this explainer. Today, we're unpacking the absolutely fascinating mathematics behind how computers actually identify and categorize three-dimensional shapes. We're going to be leaning on some really foundational research presented by H. Folds and G.R. Dreven, which gives us a brilliant look under the hood of 3D rendering. Here is our roadmap for today. First, we'll look at the WSCG 2011 conference. Second, finding the digital fingerprint. Third, the problem of pose. Fourth, the PCA solution. And finally, creating the final descriptor. All right, let's kick things off with Section 1, the WSCG 2011 conference, and the origins of this research. So, this research was featured at the 19th International Conference in Central Europe on Computer Graphics, Visualization, and Computer Vision, which is commonly just known as WSCG 2011. Now, this wasn't just some purely academic gathering happening in a vacuum. It was backed by massive industry heavyweights. We're talking NVIDIA, Silicon Graphics, Microsoft, and the reason these corporate giants pay such incredibly close attention to this specific flavor of mathematical research is because 3D shape identification is the absolute bedrock of computer graphics, gaming, and VR. The math we're digging into today is quite literally what allows big tech to build the vast digital worlds we play and work in.
Moving right along to Section 2, finding the digital fingerprint and categorizing 3D objects.
And this brilliantly illustrates our central theme for this whole explainer. Folds and Dreven put it perfectly. They wrote, shape descriptors are used to identify objects in the same way that human fingerprints are used to identify people. I mean, just think about that for a second. It's like a detective lifting a fingerprint from a crime scene to zero in on one specific suspect. Computer scientists are doing the exact same thing. They extract mathematical features from a digital object to uniquely identify it out of millions of other shapes. This whole fingerprint analogy is going to be our guiding light from here on out. So what actually is this digital fingerprint? Well, in computer science, it's known as a shape descriptor, or sometimes a feature vector. It's essentially a highly structured mathematical vector. You get it by applying specific math functions to the raw digital representation of an object. The ultimate goal here? We want to find functions that spit out a descriptor so unbelievably precise that it can uniquely identify, or at least confidently classify, that exact object. Once the computer has this descriptor in hand, it can figure out the similarity between two different objects just by applying a distance function between their descriptors. If that mathematical distance is practically zero, boom, the computer knows it's looking at the exact same shape.
But hold on, before we can even extract that fingerprint, we really need to understand the raw material we're working with here. The underlying data takes the form of 3D triangle mesh models. Basically, any digital object you see is approximated by a collection of structured triangles acting as the faces of the model. To keep track of this whole geometry, the computer uses two main matrices, an n×3 matrix for the faces and an m×3 matrix for the unique vertices. Honestly, it's basically a massive, insanely complex game of connect the dots in 3D space, where these triangles share common sides and points to build a solid form.
Which brings us to Section 3, the problem of pose and matching rotated objects. Now, I want you to consider this for a second. What happens when you're trying to match two identical objects, but they don't share the exact same pose? Imagine a digital coffee mug sitting perfectly upright on a virtual desk, and then another identical coffee mug lying completely on its side. To us, it's obviously the exact same mug, right? But to a computer that's only reading raw vertex data, those matrices look completely different because all the spatial coordinates have shifted. If your shape descriptor isn't invariant to translation and rotation, your computer is going to completely fail to recognize that those two objects are identical. So we desperately need a way to standardize the pose before we ever try to take the fingerprint. Enter Section 4, the PCA solution, or how we normalize object pose. To solve this massive headache of objects facing all sorts of different directions, researchers turned to a tool called Principal Component Analysis, or PCA. You might actually hear it called the Hodling transform or the Kerhunen-Louvre transform in some circles, but for our purposes today, just think of PCA as an incredibly powerful auto-aligner. It acts as this absolute mandatory pre-processing step.
By running PCA on the triangle mesh before we ever calculate the descriptor, researchers ensured translation and rotation invariance. It essentially guarantees that similar objects are going to have similar orientations, setting us up for an accurate match.
So the crucial point is how this auto-alignment actually goes down in 3D space. PCA uses eigenvalues and eigenvectors calculated right from the object's vertices. It effectively rotates the object so that its first principal axis aligns perfectly with the x-axis, the second aligns with the y-axis, and the third snaps to the z-axis. When all is said and done, the absolute largest variance of the object's mass is sitting right there along the x-axis. It's a beautifully elegant solution for, well, almost all shapes. But we do have to impartially note a really interesting quirk the researchers identified here. PCA struggles with highly symmetrical objects. Think of a perfect sphere. Because the mass is perfectly distributed everywhere, the eigenvalues are practically identical. This means even a microscopic, tiny variance can cause those eigenvectors to flip dramatically, which causes alignment errors for perfectly symmetrical shapes.
All right, let's wrap this up with Section 5, creating the final descriptor and inking that digital fingerprint. To actually ink this fingerprint, we need to bring in a new tool and contrast it with what we just learned. PCA, as we saw, was all about spatial auto-alignment, right? It was fixing the physical rotation in space. The Fourier transform, on the other hand, does something completely different. It's been used forever in signal and image processing to convert spatial data into the frequency domain. So by applying the Fourier transform to our nicely aligned 3D object, it maps out all the unique frequency variations of the object's surface. That is what actually gives us the hard numbers for our feature vector.
Let's move to and see how this builds into the researcher's exact methodology, the complete fingerprint pipeline. Step 1, just like we talked about, is centering and orienting the object using PCA. Step 2 is where we measure the centroid distance. That literally means calculating the distance from the very dead center of the object, shooting straight out to various points on its surface across all different angles. Step 3 involves taking all those thousands of distance measurements and organizing them into a highly structured spatial data matrix, what's known as a theta-phi matrix. And finally, Step 4. The Fourier transform is applied to that matrix, and the magnitudes of the resulting coefficients are calculated to form the final digital fingerprint. Once that Fourier transform does its magic, we're left with this huge set of coefficients. Now, the lower order coefficients represent the low frequency, large amplitude variations. Think of this as the broad, general shape of the object. The higher order coefficients, however, represent the high frequency, small amplitudes, the really tiny, intricate surface details. But to make this descriptor actually efficient, researchers don't just keep every single number. That would be massive. Instead, they only keep the first K values. K acts as this threshold. It represents the absolute lowest number of coefficients a computer needs to confidently, uniquely identify the object, without wasting precious processing power. Which leaves us with this final thought. Knowing the incredible precision required to align, measure, and extract all these specific frequency coefficients, how does this 2011 fingerprinting math form the unseen foundation for the vast 3D modeling, gaming, and VR worlds we interact with every single day? Every single time a modern physics engine calculates a collision or rendering software categorizes a background asset, it's relying on these exact fundamental concepts of shape descriptors. It's a pretty brilliant reminder that the spectacular, sprawling digital worlds we explore are built entirely on elegant, structured mathematics. Thanks so much for joining me on this explainer, and keep exploring.